Let's start the lecture. Now, the problem of the minimum energy, well, it's just the eigenvalue problem. You see, on one hand, what we have for the free particle, h, the Hamiltonian was p squared over 2m. The minimum value of energy is 0. So we just solved the eigenvalue problem, and that is what we find. For the harmonic oscillator, that's the problem we will start studying now. The Hamiltonian is p squared over 2m plus 1 over 2 and omega squared x squared, or let's say one-dimensional harmonic oscillator. The minimum energy is h bar omega over 2. Well, if you remember your midterm question, we basically obtained this h bar omega over 2 using the energy uncertainty relation. You see, if you have a particle, if you have a free particle, the energy eigenstates can be anywhere. In a sense, delta x is infinite, whereas delta p hence can be 0. If delta p can be 0, if you take p to be delta p, then the Hamiltonian can be 0. But for the harmonic oscillator, delta x depends on the energy. You see, if the energy of your particle is somewhere over here, this is more or less your delta x. It is somewhere over there. So a delta x is not infinite. So a delta p should be larger than 0. So the particle should always have some momentum. So this is one of the main distinctions between the free particle and the harmonic oscillator. So you cannot have, you see, the ground state. If the ground state was 0, the particle should be more or less over here. Delta x goes to 0. But if delta x cannot really go to 0 without increasing the energy, because delta p should increase in that case. So in that case, there is some kind of a minimum optimized value for delta x and delta p. But in that also makes the Hamiltonian non-zero. So that's why you have the minimum energy. And in fact, we will see other examples in which if your particle is somehow bound in position, in that case, delta x minimum energy cannot be 0. Well, the particle in a box example, you see, in that problem, we also had the zero energy solution because we imposed the zero boundary condition. If we had imposed periodic boundary condition. Well, periodic boundary condition basically tells us that our particle can be anywhere in the universe. It doesn't necessarily be in our volume. It just makes the periodic boundary condition just makes sure that if my particle leaves my box, then there's an identical particle that enters my box. So in that sense, the periodic boundary condition does not restrict the position of my particle within that volume. And hence I get the zero energy solution. But if I would impose zero boundary condition, in that case I would know that my particle is definitely inside my box, then I won't get a zero energy solution. The minimum energy will be non-zero. Again, just basically the reason is this one. If you impose zero boundary condition, you are basically restricting the value of delta x to some finite value. But that means delta p should be larger than 0. If delta p is larger than 0, then my particle cannot have definite zero momentum. In fact, in the case of the particle in a box, delta, if I impose zero boundary condition, my eigenstates will be just standing waves, one having momentum in one direction and the other one having momentum in the opposite direction. So there will be an uncertainty in the momentum. It will be either plus some value or minus that value. So that is where I get the delta P, non-zero delta P. Other questions? So let's look at the harmonic oscillator, first one-dimensional harmonic oscillator. Well, the Schrödinger equation that we are basically trying to solve will be minus h bar squared over 2m d squared psi by dx squared plus 1 over 2m omega squared x squared psi. This should be equal to E times psi. You see here you have many parameters that have various units. Most of the time, the first thing that you use is just go to dimensionless units. Let's see, what is the value of h bar squared over 2m, unit of h bar squared over 2m? Now I can just tell it from this equation. It should have the same unit of E times x squared. You see h bar squared psi is everywhere, so whatever is multiplying psi should have the same units. So h bar squared over 2mx squared should have the same unit of E. Well, this tells me that this has the units by the way, I'm almost done. Let me use a different thing. This has the same unit as h bar squared over 2mx squared should have the same unit as 1 over 2m omega squared x squared. These two should have the same units. Now I can make some simplifications. Well, tools do not change the units. H bar squared over m squared omega squared should have the unit of x to the 4. So let me define x0 to be square root of h bar over m omega. And x to be x0 times, let's say, u. So u will not have any units. So my differential equation now becomes over 2m. Well, derivative with respect to x is derivative with respect to u multiplied by 1 over x0. d squared psi by du squared plus 1 over 2m omega squared x0 squared u psi should be equal to E psi, or plus d squared psi by du squared plus minus m squared omega squared over h bar squared x0 squared u squared psi should be equal to 2 minus 2m x0 squared over h bar squared E psi. But you see, the way we chose x0, this is just 1. Let me just call this number, all of it, epsilon. So epsilon is equal to minus 2m x0 squared over h bar squared E, or let me call that minus E. This is 2m x0 squared is h bar over m omega times 1 over h bar squared E. Well, let's see, these m's will cancel, one of these h bars will cancel. So epsilon is equal to 2 over h bar omega times capital E. Or E should be equal to h bar omega over 2 times epsilon. And now my differential equation is d squared psi by du squared minus u squared plus epsilon minus u squared psi should be equal to 0. Now you see, nothing here has any units. Epsilon is unitless, u is unitless, dimensionless. So this already tells me that the energy of my state has to be h bar omega over 2 times epsilon. Epsilon should be just some number. We don't yet know that, well, we already know what that number is, but even if we didn't know the solution, epsilon will just be some number. 1, 1.5, 1.3, because it's an eigenvalue equation of an operator that doesn't have any parameters in a sense. You change omega, the equation for epsilon doesn't change. You change m, the equation for epsilon doesn't change. So epsilon, it will be independent of m, h bar, or omega. So we already know that if you double the w, if you double the frequency of the harmonic oscillator, the energy eigenvalue should be doubled. We can say that without even solving the solution, solving the equation. Now we need to solve this equation. Are you familiar with how to solve the eigenvalue equation for the harmonic oscillator? Yes, no. I mean, depending on your answer, I will go into some details or not. Okay, everybody is waiting somebody else to answer. Okay. Okay, she doesn't want, so if you don't say yes, I will not go into the detail. You are not familiar. Okay, you are not familiar. Okay, let's solve this differential equation. Now, basically what we know is we are looking for normalized solution so that the wave function should go to 0 as u goes to infinity. So that is something we want. So let's look at how my differential equation or the solution of my differential equation behaves as it goes to infinity, as u goes to infinity. Well, the derivative stays. But epsilon will be some number. It will be fixed. It will be, whatever the value is, as u goes to infinity, it will be negligible. So close to infinity, this is the equation that governs the behavior of my wave function. Now let me try this one, psi. Let's say it's e to the power minus u squared over 2 psi, some psi 0, some constant. I claim that this is a solution of my differential equation. It's not the exact solution, but this is the solution in the limit u goes to infinity. Now, in fact, plus minus u squared over 2, both signs are solutions of my differential equation. Let's check. Derivative of psi with respect to u is just plus or minus u psi. And if you take the second derivative, this is, well, derivative of the first one, psi minus plus minus psi, plus minus u times the derivative of the second one is plus minus u times psi. So this is u squared psi. The first term will be negligible compared to the second term, because I'm looking at the limit u goes to infinity. So d squared psi by du squared is approximately u squared times psi when u goes to infinity. So this is indeed the solution of my differential equation in the limit that both of them are solutions of my differential equation in the limit that u goes to infinity. Now, of course, not both of those solutions are acceptable. So I'm looking for a solution that is normalizable, and hence it should go to 0 as u goes to infinity. But that means only one of these solutions are possible, not both of them. So I'm looking for a solution which at infinity behaves like this one, minus sign, not the plus sign. Well, of course, this is not the exact solution. This is the solution only as u goes to infinity. Let me just put some, multiply this with some function of u. So at least this will tell me that as long as phi of u doesn't go to infinity as e to some power of u squared, this will be a normalizable solution of my differential equation. So I will need to determine what phi is. That will be my next task. Well, let's look for the differential equation satisfied by phi. Derivative of psi with respect to x will be minus u times psi. Let me write it in this form. Plus e to power minus u squared over 2. Derivative of phi with respect to u. Sorry, I'm taking derivative with respect to u. This is the first derivative. Now the second derivative of psi with respect to u will be minus psi plus u squared psi. This is the derivative with respect to u of the first term. No, sorry. Okay, let me not be lazy. Okay, let me take the second derivative now. This is minus e to power minus u squared over 2 phi plus u squared e to power minus u squared over 2 phi plus minus u e to power minus u squared over 2 d phi by du. This is the first term. Now the derivative of the second term is minus u e to power minus u squared over 2 d phi by du plus e to power minus u squared over 2 d squared phi by du squared. Let me put this in my differential equation. Now remember, my differential equation for psi is this one. Let's see what I have. Well, all the terms have that e to the power minus u squared over 2 term. So let me just multiply this expression by e to the power u squared over 2. This should be 0. Because the expression in the rectangular brackets is 0. This is equal to, well, let's start the first term, minus phi. I'm writing the second derivative, the first term. Now the second term, you see the second term is u squared phi, but here I have a minus u squared phi. They will cancel. So this term will be cancelled. This term will be cancelled by this term over there. So I don't write it down. Now the third term, I have two of them. 1 and 2, they are the same. So it's minus 2u d phi by du plus d squared phi by du squared plus epsilon phi. This is what remains. So let me rewrite it. D squared phi by du squared minus 2u d phi by du plus epsilon minus 1 of phi should be equal to 0. So I need to find the solution of phi which satisfies this equation. And with the boundary condition that it shouldn't go to infinity faster than e to the power u squared over 2. Because my wave function is this phi multiplied by e to the power minus phi u squared over 2. If phi doesn't go to infinity faster than e to the power minus u squared over 2 going to 0, then the result will go to 0 at infinity and I will have a normalizable solution. Well, let's look for a solution in the form of a polynomial. A Taylor expansion, that's what I will do. Assume, Well, you see, this doesn't have any singular points. So it's a nice polynomial, it's a nice differential equation. So phi of u is equal to a of n u to the power n. If you just put it over there, n from 0 to infinity, what you have is a n times n minus 1 u to the power n minus 2, minus 2 n from 0 to infinity, a of n u to the power n, plus n from 0 to infinity, epsilon minus 1 u to a n u to the power n. Now the coefficient of u to the power m0, 1, etc. This should be 0. Now on the left hand side, the coefficient of u to the power m is just a n plus 2, n plus 2, n plus 1. That is from the first term, minus twice a m times m plus epsilon minus 1 a m. This is the coefficient of u to the power m on the left hand side. On the right hand side, the coefficient is 0. So this should be 0. Hence, a of m plus 2 should be equal to 2m plus 1 minus epsilon a m over, this is m plus 1 times m plus 2. So this is how various coefficients will be related to each other. Well, you see, I get two solutions. One, if you know am, you know am plus 2. So if I know a0, then I know a2, I know a4, I know a6, I know all the even n. If I know a1, then I know a2, a3, I know a5, I know a7, I know all odd n. Well, I'm looking for a second order differential equation. It should have two independent solutions. One will contain the odd powers, the other one will contain the even powers. So these are the two solutions I have. Well, let's see. This is okay. So phi of u just becomes a0 times m even am over a0 times u to the power m plus a1 m odd am over a0 u to the power m, a1. Those two terms are my independent solutions, the two independent solutions. Now let's see how these solutions behave for very large values of u. That is what I need to check. I need to make sure that none of those solutions diverge faster than e to the power u squared. Now I will just sketch it. Now I need to go to my other lecture, but we will continue on Wednesday. You see, for large m, a m plus 2 is approximately a m over m. Do you agree? Well, you see, for large, this is my relation. If m is very large, epsilon is negligible, 1 is negligible. Oh, I also have 2. Now, A of 2n, this is even m, will be approximately, let's say, let me write it in this form first. This will be approximately 2 over 2n, A of 2n minus 2. Well, this will be approximately 1 over n minus 1, A of 2n minus 4. So A of 2n will be somewhat 1 over n factorial A0. I will be more precise on Wednesday. Now let's see m even. A of m over A0, u to the power m. This is equal to sum over n, A of 2n over A0, u to the power 2n, and now from 0 to infinity. This is equal to n, well, that is 1 over n factorial, u squared to the power n. This is equal to exponential of u squared. So it diverges faster than e to the power minus u squared over 2. Of course, here I made one assumption. I assumed that m can get very large and a's will never be 0. That was my assumption. Well, that assumption cannot be true. My sum should have a finite number of terms if I don't want it to diverge. So my am terms should terminate at some value. And so if they are terminate, that basically means that you see, epsilon should be equal to twice some integer plus 1. So if that is satisfied for some integer, all the a's after that integer will be just 0. They will not go as 1 over m. They will just be 0. m0, and hence the energy of this level will be h bar omega over 2 twice m0 plus 1. So again, imposing the normalizability gives us discrete energy eigenvalues. And how did I write this one? Well, you see, if you go back, this is how energy of my eigenvalue relates with this parameter epsilon. Now, as I said, we will repeat this on Wednesday. So if you couldn't follow, don't worry. On Wednesday, we will repeat and we will be more formal. Now, any questions? Okay, so see you on Wednesday.